Hello, calculus students and general seekers of truth. Welcome to the continuing video series on Taylor series error-bound approximation. And we get to this very important theorem that bears many, many names. Okay? But let me just explain a little bit about what this says before I give you all the different names for this. So this says that the remainder of the nth degree Taylor polynomial of any function is equal to the n plus 1 derivative at some point c of x minus a, and the rest of this stuff here is just the general form for the Taylor series. Okay, but the key point here is c. So this is really saying, like, there exists a value c between x and a, okay, such that this is true. And this is a kind of an amazing thing that it says, is that we could potentially find the exact error or the exact remainder of a Taylor polynomial approximation if we could find out what c actually is. Okay? So it's like saying, okay, the center here is at a of the Taylor polynomial, of the Taylor series. We are going to use the nth degree polynomial of the Taylor series to do some sort of estimation. And if we were to do that, then in fact the remainder or the error is exactly equal to this, if we could find out what that point c actually is. Now I should make a note here that we usually, and in fact hardly ever, know the value of c. Okay. But we can often set or find an upper bound for f, or the nth plus 1 derivative of c. Okay, so we can't always know, in fact we hardly ever know what the value of c is equal to, but we can say something like, oh, the nth derivative of f at c must be less than or equal to some number. Okay, so we can usually find this m, this constant m, that is larger than the nth plus 1 derivative at the point c. Let me clear this up here. This should say. Okay, and then if we can do that, then we can in fact set the remainder as less than or equal to something. In other words, we don't know the exact answer, and in fact if we did know the exact remainder, we would be able to find the exact answer of f. So I mean, then that makes the Taylor series really unnecessary. But most of the time we don't really know what c ever really is. We can just set a maximum on it. Okay, I'm going to post a separate video that explains the proof, or at least the rationale behind this theorem. It's a little bit lengthy, so I want to omit it from our continuing series here, so that we could move on to just using this. But I will post a video that explains the rationale behind this theorem, so that you can see that, you know, where this idea really comes from. Now the different names for this. This is called the Lagrange error bound. Okay. This is also called Taylor's remainder theorem. Okay. And this is also sometimes called the Lagrange form of the Taylor series error, Taylor polynomial error. Okay. So Louis Lagrange and Brooke Taylor sort of developed this idea around the same time, and they're both given credit for this. And again, the idea is we're going to use this theorem. We don't ever really know what C is really equal to, but we can set an upper bound for it. And that means if we set an upper bound for this value, then we can also set an upper bound for the remainder, or the error, for r sub n of x. Okay? Alright, so I'm going to end this right here, and we'll pick up the example in the next video.